So, good morning everybody. So, we start the reinforced morning, and it's a great pleasure to introduce Jean Bertoin from the University of Zurich, and he's going to speak about reinforced Galton-Watson processes.
Oh, thank you, Christophe. First of all, of course, I would like to thank the organizer for putting together great talks, and it's a pleasure for me to be here. So it's a talk about reinforcement, and it's a joint work with Bastien Malin from Toulouse. I will mostly do a talk on the blackboard, so if you don't mind, I will just switch off this stuff. So the reinforcement in the title refers to a set of methods which play an important role in many sciences nowadays. So these methods, roughly speaking, aim at increasing the likelihood of certain evolutions in systems. So this can be artificial systems or natural systems. So probably the best known is in the field of learning. So for instance, in artificial intelligence, you have deep learning or learning by reinforcement. But it also works for natural systems. So as professors, we are used to repeat again and again important results to our students. And we also intend to motivate them by giving them good grades when they are successful, and maybe not so good grades otherwise. And closer to our field, in the framework of stochastic processes, this was introduced something like 40 years ago by Coppersmith and Diaconis in a paper which has never been published, but it is very influential. And roughly, I never saw the paper, so it's just I'm just saying things that I heard. It's the purpose of Coppersmith and Diaconis was to modify the random walk on a graph by making transitions which have occurred often in the past, even more likely to occur in the future, more likely to be repeated. In the last couple of decades or so, it seems that reinforcement has been observed in demography for human populations, and it's sometimes referred to as intergenerational transmission of fertility. So what does that mean? It's the observation that you have already made. If in your family, if your parents, your grandparents, and your ancestors had a large sibling, then yourself, you are more likely to have more children than fewer. So it seems that there is some reinforcement occurring there, and there are many possible explanations. So one could be a social economical reason, it could be also cultural, it could be also genetic, but it's not so important for us. So what I would like to do is to introduce a very simple model of reinforcement in the setting of branching processes, and try to analyze how this reinforcement affects properties of the branching process. So to be more specific, we will consider new probability measure. So this will be the reproduction law. We start from. And I will always assume that this is a probability measure on the set of non-negative integers. And I will always suppose that it has a bounded support. So for instance, this means that an individual cannot have more than, say, 20 children. And on the top of that, there is a parameter Q between 0 and 1, which will be called the memory parameter. And essentially, it measures the strength of the reinforcements. So in the limiting case, Q equals 0, you have no reinforcement, and the process will simply be a Galton-Watson process. And in the extreme case, Q equals 1, you have full reinforcement, and actually individual keep repeating what occurred at the previous generation. So the things run as follows. So you start from an ancestor, and let's say that you consider an individual at a large generation n, well, large or not large. And the way this individual reproduces is as follows. So with probability Q, the reinforcement probability, it will reproduce according to the empirical offspring distribution on its ancestral lineage. So with probability Q, you will essentially pick at random one of the ancestors on the lineage, say for instance this one, and if this ancestor had 3 children, then you reproduce exactly the same. And with complementary probability 1 minus Q, then you decide to reproduce according to the reproduction. So with probability Q, 1 minus Q, then reproduce according to the distribution. So is the model clear? Okay. So if you think a little bit about this model, then you will soon realize that the key properties of branching processes that you are used to work with are destroyed. Because if you consider, for instance, 2 individuals at a generation, a given generation, then they will share some ancestral lineage, not completely, but part of it. And this, this destroys the branching property. So with this type of process, branching property is lost. You have a memory, a full memory of what your ancestor did, and it makes the study quite challenging. Even very simple questions, which you could ask about branching processes, Galton-Watson processes, will be difficult in this set. Okay, so this model, I will call it a reinforced Galton-Watson process. Yep. And the question I would like to address, probably the simplest and nonetheless quite fundamental, is to try to understand how fast grows the population in terms of generation. And I would like actually to investigate the expected value of Z of n. Okay, so where Z of n is my reinforced Galton-Watson process. And I would like to understand how this grows or decays as n goes with infinity.
What is Z of n exactly?
Sorry?
Is it the population size?
It's a population size at generation n. And to be a bit more specific, actually, you see that in these models, the ancestor will play a very important role. And I will denote with a subscript L when the ancestor has L children. So here the probability PL corresponds to the fact that Z of 1 is equal to L, the ancestor has L children. So maybe as a benchmark, we can recall what happens in the case of the ordinary Galton-Watson process. If you are teaching a course on Galton-Watson process, probably you will not even prove this result. I mean, you will leave it as an exercise for the students because it's fully elementary. So in the case Q equals 0, that is for the original Galton-Watson process, what you know is that actually it depends a little bit. Let's say that the ancestor has also a number of children distributed according to nu, then expectation of Zn is exactly m nu to the n, where m nu is the mean reproduction number. It's the sum of k, nu of k. And so let me state right now the result. And the rest of the talk will be dedicated not fully to the proof, but to the main ideas of the proof. So what is the result? We need to introduce some notations to recall that the reproduction law has bounded support, and I will denote by k star the upper bound of the support. So let k star, this is the maximum of the k's such that nu of k is strictly positive. And there is also a parameter beta, which will be 1 plus 1 minus q nu of k star divided by q. Okay, so far not too bad. And now there is a more complicated object. I denote it by m, nu, and q. And it's given by q divided by the integral from 0 to 1 over k star. It's an integral with respect to dt. And then the product will be taken over the support of the reproduction law of 1 minus tj to the power nu of j 1 over q minus 1. And the theorem is as follows. So first, in the case when you start with, when your ancestor has a maximal possible number of children, then for L is equal to k star, then the expected value of the population at time n is equivalent, so that's yes, in the usual sense. There is some constant which can be made explicit, but it's not so important for us. Strictly positive, and m mu q of n. So essentially, this means that this strange quantity m is the effective reproduction average of your population. So that's, of course, as n goes to infinity. And for L, which is not the maximal number, then there is actually a correction, a polynomial correction. So there is another constant, explicit also, but it's not so important, n to the power minus beta. Beta is above. Beta is greater than 1. And then the same exponential factor.
Can you say what's the limit of m mu q when q goes to 0?
Absolutely. So as q goes to 0, then you recover the mean m nu. And on the other hand, if you let q go to infinity, q goes to 1, then you recover the k star, the maximal number. So it's something between the mean of the reproduction law and the maximal number. And it can be proved, it's not obvious, I think, from this formula, but it can be proved that it's monotone increasing in Q. Okay, so what do we learn from this result? I think two things. Well, first, that the reinforcement has indeed a very significant impact on the evolution of the Galton-Watson process, simply because, well, it's never the case for Galton-Watson processes that the reproduction number of the ancestor plays a role in the asymptotic. I mean, you never see such polynomial corrections in Galton-Watson processes, even in multi-type Galton processes, which are irreducible. The second information, of course, this comes afterwards. But when you look at the formula, probably it does not resemble anything you saw before in this setting. So most likely, even though the problem, the model looks very simple, well, you won't have a simple way of getting to this quantity.
Why is it the case that only the first generation? Why not the second generation? Why does it matter the number of individuals in the second generation?
It's essentially it's because it's the one which will repeat it the most.
Why not the second?
The second will also appear, provided that actually it's also equals to K star. So what we now know is that the strategy of the Galton-Watson process to get a large population is at the early stage of its reproduction to have only K stars.
I understand, but why early? Why does early mean 1?
Sorry?
So why does it mean the first one? So if the first one is small, say L is equal to 1, but the second one is K star, why
it will still have an impact because the first one will be repeated more often than the second one. And you can, actually, the process never loses, this type of process never loses memory. You can not fully recover the, let's just stick to the case of Galton-Watson processes. You can, even if you don't start with K star.
Start with 1, the smallest possible, and have maximum in the second.
Absolutely. Then there will be this correction.
Which one? The second.
The second one, yes. You are in this phase.
But that's what I'm puzzled. Why it doesn't matter that in the second generation you have that? Okay.
Calculation also. It's okay.
I think you basically average over the second generation. It's like a new. You don't condition on the second generation.
Sorry?
You don't condition on the second. You take
no. You just yes. Absolutely. Yeah.
So it's averaged out.
So if you don't condition on the first generation, then you still get, I guess,
if I condition on the first generation?
If you don't condition on the first generation.
Essentially, yes. If we don't condition, if we assume that the initial number of children is random according to nu, then it's the first one, because there will be one individual with, with probability, strictly positive probability. Your ancestor will have K star children. And therefore, this is this behavior which prevails.
Stas is also this.
Sorry?
Stas says that's
okay, so perfect. Okay, so yeah.
The bounded support. So if you have even very light states, you have.
Okay, so that's. I would have liked to answer this question for the question, but it's okay. Maybe it's a good time. You have a fully different behavior when the support is unbounded, and actually the growth of the expected population is no longer exponential; it's super exponential as soon as the support is infinite, because there is a tiny probability that you will have a huge number of descendants at the first generation, and Q is fixed. So among those huge number, a lot of them will repeat and again and again. So you easily see that when the reproduction law has unbounded support, then the behavior is super exponential. We know precisely how it is, say, for instance, in the case of gamma type distribution, but it can even explode very quickly. So for instance, if the reproduction law has finite moments of order, let's say 1,000, then actually the expectation of Zn will explode after time n equals to 1,000. Because there is a tiny probability that you will keep repeating the bad thing. Okay, so yes, as I was saying, it's likely that there is no quick proof of this such a result. And I must say that actually we would never have come to the solution if there was not a paper by Philippe Flageolet and co-authors. So there is the method that I will describe, and which is probably at least, well, it's more interesting than the result itself. It's due to Flageolet and co-authors, and a paper published in 2005. In the Annals of Probability about analytic errors. And even though, strictly speaking, I mean, the results of Flageolet do not apply to us, the philosophy that he developed plays a crucial role. Okay, so what are the main steps, which I would like to present now? And the argument uses actually quite a number of different techniques. The first of it is from combinatorial nature. So it's something which is well known when studying trees, that you can describe the size of a tree at generation L in terms of the so-called many-to-one formula. So what is this many-to-one formula? It's something, it works for deterministic trees. So you consider any rooted tree, for instance, something like this. Maybe you have this. And you are interested in counting how many vertices you have at generation n. So what you do is the following. You start from the ancestor, well, you have no choice, and you record the number of children of the ancestor. So you start, let's call it, this is my tree T. So you record the number of children of this ancestor, and then you pick one of the children of the ancestors uniformly at random. Say, for instance, you select this one, and then you count how many children have the selected child. Only one, so you record it. You have no choice. You select that guy, and then you count how many children it has, and so on. And you keep doing this. Okay, so the formula, the many-to-one formula, in this setting, so it does not use any branching property, it's true in full generality, is that when you start with L children, expected value of Zn can be expressed as L, so that the number of children of the ancestor, times expected value of eta1. So eta1 is the number of children of the child that you have chosen uniformly at random, times eta2, etc., times eta n minus 1. Okay, so where eta j is the child, or the individual, or the vertex selected at the jth generation. Okay, so why is that possibly a good starting point? It's due to the dynamics that we introduced on the reinforced branching process. Because you can now analyze the sequence eta j. It's given by essentially a Fourier urn with random replacement. To be more specific, if you compare, if you just recall the definition of the Galton-Watson process with reinforcement, you can imagine that you have an urn which represents the number of children of your forebears, and at each step you pick a ball uniformly at random in the urn. So this corresponds to picking an ancestor uniformly at random on your ancestral lineage. And then, so you pick a ball, a ball of the urn, and you replace it, you observe it, there, you replace it into the urn, and you add with probability Q a copy of that ball. So that's a reinforcement step. And otherwise, you put a random sample of your reproduction rule. Otherwise, a sample. With load. Okay, so I hope that it's clear. We are just repeating the dynamics of the process. And therefore, you have a formula above. And you say, OK, now it's piece of cake because Polya was a very famous guy. His picture is on the photo there on the wall. And the Polya urns have been around for more than 100 of years. So estimating this quantity, just look at your favorite books on Polya urns. You don't find anything. You don't find anything because what people have been looking most at in the setting of Polya urns are kind of law of large numbers and central limit theorems, so fluctuations of urns. And it concerns additive properties of the urn. So instead of taking products of those balls that you put successively back in the urn, you rather look at sum of direct masses of the ball. And so the problem actually is not really a problem of the strong law of large numbers or fluctuation. It's much more a problem of large deviations. Okay. And that's where the techniques by Flageolet came into play. So I struggled a bit with this, found the paper by Flageolet, and he had a route for obtaining such large deviations. So how do you... OK, that was not part of Flageolet's idea, but nonetheless, it gives something related. The second ingredient, how would you analyze such urns? There is an old paper by Atreya and Carlin, in the 68, I think. It was part of Atreya's thesis, in which they make a very important connection between urns and branching processes, multi-type. Branching processes in continuous time. I will not explain the idea of Atreya and Carling, just give it in our setting because it makes things much easier. So the idea is instead of looking at the urn step after step, you will look at it in continuous time. So you will add balls continuously. And to be more specific, let me introduce little y of t for t greater than or equal to 0. This is a so-called standard dual process. So it's a process starting from 1, and then you jump at 2, and then you jump at 3, and so on. So the waiting time between the first jump is, for the first jump is exponential with parameter 1. Waiting time for the second jump is exponential with parameter 2. For the third jump, exponential with parameter 3, and so on. So there is an acceleration of the process. And it corresponds to, if you are more familiar, well, probably all of you know what Yule processes are, but if there is one person who doesn't know, it's a pure birth process such that the rate of birth from state n is exactly equal to 1. So you transform now your urn process into the following. So you denote by y j of t. This is the number of balls of color j that you have at time t in the urn. At time t. Okay? Is that clear? So I did this acceleration of time. And it turns out that the process y of t, so that's the collection of the y j of t, and you do it for all t non-negative. This has a very nice structure. Actually, it's a branching process in continuous time. So it's multi-type because the types are the j's, possible number of children, branching process in continuous time. And the reproduction is very easy too. We are always doing the same. So each individual reproduces at rate 1, no matter what its type is. With probability q, it produces a copy of itself. And with probability 1 minus q, it produces an individual whose type is distributed according to u. Okay? So it's each individual reproduces independently of the other at rate 1 and gives a copy that is a child with the same type with probability q, and it gives a child with type random type distributed according to u with probability 1 minus q. Okay. And so if we rephrase the analysis that we have made before, and we use also the well-known fact that the original Yule process at the one which counts the number of balls at time t, this has a geometric distribution with parameter exponential minus t, so that's a classical fact of the volume process. What you obtain is the following. So you are interested in expected value of your reinforced Galton-Watson process, the n, and you consider actually you form a generating function, generating transform of it, n minus 1, sum for n equals 1 to infinity, to the minus t. And this is exactly the expectation in terms of the multi-type branching process there. The expectation when you start with one individual of type L of the product of j, y, j. So why? So it seems that you are making things a bit more complicated because now you are working with generating functions instead of the quantity you are interested in. But the nice thing is that you have now tools from stochastic analysis to analyze the right-hand side. And the point is that for general branching processes, so let me introduce the following notation. You see right now, the number of individuals has been kind of, it does not play so much of a role. We can treat branching processes having this type of dynamics without paying too much attention of the type, because the type plays no rules in the dynamic of the process. So let me see better use an index A. So A is a collection of AJ, and in the calculations that I will made in the end, the AJ will be simply equal to J. But it's easier to treat this more abstract setting. So, and you consider the probability generating function of the whole process, ML of A and T, so that this is exactly its expected value starting from L of the product of AJ, YJ of T. And I'm saying that this probability generating function satisfies a differential equation. And the differential equation, so I will write it now, take the derivative with respect to time, ML of A and T. This is equal to ML of A and T times Q ML of A and T plus 1 minus Q, the scalar product of nu and M of A and T minus 1. Okay, so for those who are familiar to work with continuous time branching processes, this should be pretty obvious. What does this equation mean? So you look at the first birth event of your branching process. So either you produce a copy of the ancestor, so this occurs with probability Q, and this corresponds to the fact that you get this quantity multiplied by the same quantity. Or with probability 1 minus Q, you produce an individual with type distributed according to mu. You still have, of course, the initial ancestor, but this gives rise to the second one, and you subtract one. So that was the second time that when we got this, I said, okay, now it's easy, because it does not look so terrible. So we will simply resolve this equation, and we will get our solution. And so it's nonlinear, okay, no big deal. But the problem is that it's really multidimensional. So I tried quite a time without getting anywhere. I asked for help in Zürich. There are specialists of differential equations, they are good ones. And well, they didn't help that much. I lowered my ambitions. So I said, okay, maybe I will be happy. Just tell me, depending on A, whether this quantity goes to infinity, explodes, or goes to 0, because this is really the question I would like to answer, and nothing. And so I was a little bit desperate, and someday Bastien sent me an email and said, okay, I think I have a solution. Okay. And a week or two later, so he sent me papers by mail, half a dozen of pages, and with a solution, something, I will not write down the solution, but I tried, of course, immediately I started to read the text. It took me maybe a couple of days, and after a couple of days, well, I was certain of two things. Well, first, most importantly, that he was absolutely correct, and I had absolutely no idea how he came to this solution. And so I asked him again, and he was answering, well, I don't know, I saw sometimes something a bit similar, and I did some modification. Because it was like, okay, I take my equation, I modify it this way, then I take the exponential, then I do the time change, and I take the logarithm, and blah, blah, blah. And it was like magic. Now, after a year, I think we understand it a little bit better, so I will explain the sketch of the proof. The idea is to consider this guy here as a function, phi of t, and you assume that you know it. So the nice thing is now that you have a one-dimensional equation, it only depends on the function ML. And it's known as Bernoulli equation, and it can be solved. So it's a textbook solution of differential calculus. So the way you do it is you set f is 1 over m, I think. If you do this, or 1 over m, yes, 1 over m, and you divide this equation by m squared, then you get a linear equation. It becomes a linear equation in f, depending on this constant here. Then you solve it. You can solve it. And then you put it back there, because you do not know what phi is, but you have a formula here. You put it back. And then it's a miracle, because the equation is closable, and you find another equation which you can solve, and you get find the solution. So when I say it's not really a fully explicit solution, I don't want to give it explicitly, but essentially what you get is that your function, some transformation of the function ml of a and t is given by the inverse. And then we will see the of the function x gives the integral from 0 to x dt product of 1 minus. So it will be t aj, and then u of j, 1 over q minus 1. So the one which appeared in the form. Okay, so let's do a quick recap. Can use the board there.
Can you lift the board on the right?
Sorry?
Can you lift the board, please?
Yeah, sure. Ah, sorry. Okay. So, as a recap, well, now this is what we denoted by ml of a and t, and we have an expression for it. Complicated, yeah?
Just so when t is large enough, this must be infinite, right?
Absolutely. So I'm skipping details about under the rug. So actually, you need. This is a very good point. Indeed, if the coefficients a are too large, then there will be an explosion. If the coefficient a are too small, then it will go to 0. And the most important, you can find a critical setting for the a's, and but you are right. You are there are situations in which the solution explodes, but we know exactly where when it explodes, in which case.
This radius of convergence would give you the q more or less, right?
Okay, so let's try. Let's try. Okay, so we have this, and what we are interested in that guy. Of course, in the best of the world, you could try to express the right-hand side as a generating function, but it's out of reach, of course. But nonetheless, you are only interested in the asymptotic behavior of the coefficients. And the first, well, the best known method for this is to use Tauberian theorem. So you want to replace this by some c to the n. So let's say you take t is minus logarithm of 1 minus c, so that this quantity will just be c to the n, and you want to analyze the behavior of m l of a and minus logarithm of 1 minus c. You want to analyze it as c goes to 1. Okay? And so it's doable. I mean, maybe I was too negative about the solution that Bastien obtained. It's complicated. But if you are only interested in estimating asymptotic behavior, well, this can be done because it's transformation of transformation derivative and so on. There is no big issue there. But the problem with Tauberian theorem is that it does not give you exactly what you want. It gives you something about the César mean. So it would be more like you take the sum expected value of Z1 plus expected value of Z2, etc., plus expected value of Zn. And you need some monotonicity. So you can estimate this quantity, but if you want to return to your initial problem, you need some monotonicity, which is, there is no reason why the expectation of Zn should be monotonous. And the idea, again, in flageolet, so this, that's one of his main tools in his book on is the following. Instead of looking at C as a real parameter, you work in the complex plane. You work in C, the complex plane. So the solution that you have obtained makes sense, is analytic, and actually, so it runs like this. So you have 0. You have the point 1, which is of interest. And you can check, that's easy from the definition, that the solution is ML that you have obtained is analytic without singularity on the unit disk open. The heart of the next proof is actually to show that you can do a bit better. So you can find a slightly larger disk around 0 with radius 1 plus epsilon 11. And here, so here you have your singularity. And actually, the solution will not be analytic on the larger disk pointed at 1. But it still remains true that it will still be analytic on a Pac-Man domain like this. So you have to take away a small cone, and the angle of the cone has to be less than 1. So the next step of the analysis, which of course I will not do because you would need a precise formula for M, consists in showing that the solution is analytic on this larger domain, and by analyzing the behavior of the solution as you, so there are no other critical points in this larger disk except possibly in the cone, and by analyzing the behavior of the function as you approach this singularity at 1, then you can, Flageolet and Odisco have a beautiful theory in which they obtain extremely precise expansions of the coefficient of a geometric function using this approach. If you are unfamiliar with this, at first it looks a bit magical, but it's very much in the same spirit as local central limit theorem. So you are doing, you are using the Cauchy formula and integration around some well-chosen contours, and the result pops out. Okay, so I will not give further details, but with this technique, well, you are able to prove the estimates that I gave in the theory. And I will stop here.
Other question?
Yeah, so you compute the first moment, so but what about other moments? I know you explained how hard it was, and the almost short behavior.
Yeah. No, that's okay. So we have a second work. Okay, I can explain a bit what we did afterwards. you saw that the first moment was related to this many to one formula. That was a starting point for trees. For the second moment, you need many to two formulas. And the results are a bit surprising. So they're not as complete as we wished. But again, they underline the role of the maximum number K star. So for what we have, okay, so the natural question now is you look at Zn and you will normalize it by this m mu q to the power minus m. So if you were in the Galton-Watson setting, so this would be the Kesten-Stigum theorem, and you know that it converges to a random variable, which is strictly positive as long as your process is not extinct. So in this situation, this is no longer fully true. Actually, this converges to, well, yeah. I don't know whether I should go really into details, but there are some situations in which there is a convergence in L2 of this quantity. And there are some other situations in which actually this limit is 0. Okay, so the assumption, so if, to be more specific, I think it's q k star plus 1 minus q mu is greater than 1, then this guy here is bounded in L2, and you have convergence in L2. And otherwise, if it does not hold, then the process is not uniformly integrable, and the convergence is 0. Okay. So you see, the larger K star is, the more likely you are to have this convergence in L2. And in the case when this inequality failed, well, we have no idea what the right way, the right rate of growth sample-wise would be.
Other questions? Yes.
You try to get a complete asymptotic expansion, just not one term, but two terms?
Oh yeah, the method of Flageolet is, and Odlisco is amazing because you can get as many terms as you wish. It of course requires to have an asymptotic or a good expansion of the singularity at 0 here. So you need not just the first term and then the next term, but I guess yes, this should be doable. Yeah. Theoretically, it's doable, and in Flageolet's book, yes, he uses that a lot.
But so you need to approach the singularity with an angle which is...
Absolutely. Yeah. It's not sufficient. In the usual Toberian theorem, you just approach the singularity along the line. And then you need here to approach the singularity in the complex plane with the exception of this cone. And the angle of the cone plays basically no role. It makes your life easier the larger the cone is. But you cannot exceed an angle of pi.
Questions? And extension probability, you can compute it? Or
In sorry?
Probability of extension.
Ah, that's another. Yeah. No. 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 What we know, it's still an open problem. We do not have a necessary and sufficient condition for survival, or what we learned from here is that as soon as the quantity m mu q is less than 1, then you have extinction. But we strongly suspect that this is not the necessary and sufficient condition. We have also a sufficient condition for survival, which these quantities are tough to compute. Well, you can only do numerical computations most of the time. And amazingly, the sufficient conditions that we have for survival numerically looks very close to the one that we obtained here. but it's not the same. So there is a very tiny gap, but we believe that the behavior on average is not the one which decides whether you have almost sure extinction.
Okay, thanks a lot.